let's begin this. We can start. Okay. So this is a bit going to be revision of the previous lecture. What we done in the previous lecture, we did a study about PE effect in great detail. What is a PE effect? Photoelectric effect, right? We done the photoelectric effect and the experimental setup about the photoelectric effect in the previous class. Is this clear, everyone? Got it? Good. So in this particular class, we are going to discuss about the properties of PE effect. We are going to discuss the relation between kinetic energy max and the potential, what we already done. We are going to discuss the so many properties in this related to the PE effect, obviously, because it is as it is properties of PE effect. Okay, so it is going to be a bit more theoretical. Again, we are going to see the graph between photoelectric effect and intensity and the potential effect on potential on photoelectric effect, right? And frequency related graph, and you can say the laws of photoelectric emission are what are these, and the Huygens theory, and then question. Wait. This is not the properties. Yeah, okay. So yeah, okay. So this is going to be, I think, the smallest lecture of yours today. We are going to discuss the basic theory about PE effect, what we already done in the previous class. Okay, is this clear, everyone? So let's wrap up this as soon as possible. So okay, this is your recall. In the previous class, what we done, experimental arrangement of the study of photoelectric effect. Okay, and what we seen in this particular effect, there is a photosensitive plate. In this photosensitive plate, whenever the source, or you can say quartz window, in this particular quartz window from the source, the light is going to be hit. So due to this light intensity heating, it is going to eject the number of electrons, and these electrons going to be flow towards this particular anode, and then in this particular whole circuit we get a current. Is this clear? So basic setup about it, we already done in this thing. Okay, this is your variable resistance, or you can say rheostat, variable resistance or rheostat, also known as. Okay, this is your micrometer and this is voltmeter, nothing as such. This is key, this is volt. So applying this particular circuit, using this particular circuit, what we get? We get photoelectric current. Photoelectric current. Is this clear with everyone? Clear, everyone? Good. Now, from this particular slide, the maximum things is going to be a little bit boring and a bit more theoretically. Okay. So experimental study of photoelectric effect, that's we already done. The electrons are emitted by the plate C and are collected by the plate A. This is plate, not plant. When the plate A. So this is done. When the collector plate A, where the collector plate A is positive with respect to the emitter plate C, then the electrons are attracted to it. Hence, the photoelectric current is constituted. The emission of electron cause flow of electric current in the circuit. Basically, the plate A is going to be the positive. We put a positive potential over there, and plate C is going to be the negative. So whenever the emission or ejection of photoelectrons going to be done, so due to this negative terminal, due to this negative cell or terminal of a plate, or you can say negative effect of a plate, so negative going to repel, and that is automatically the photoelectrons going to attach or going to convert, or you can say attracted towards the positive plate, and there is a flow also. So whenever the flow of electrons, the flow of charged particles is going to be done, we know the flow is basically known as, what it is known as? It is known as current. So here the current is generated due to the photoelectrons, or you can say photo emitted electrons. Okay, so that is why it is known as photoelectric current. Is this clear, everyone? Is this clear now with everyone what I'm saying? Okay. The next point is the potential difference between the emitter and the collector plate is measured by voltmeter V. Whatever the potential difference we create, that is measured by V, whereas the resulting photo current flowing in the circuit is measured by a micrometer. Obviously, that is a very normal thing to understand. The photoelect, or you can say from this particular paragraph, from this particular second paragraph, what you can get one point as a note: the range, the range, the range of photocurrent. Photocurrent is basically what particular current which is going to be developed, which is going to be generated by this photoelectric effect. Okay, the range of photocurrent is up to the order of microampere. Is microampere, simply microampere. Microampere means mu, or you can say into the power minus. You know what is a microampere, so I don't need to rewrite this thing. Clear? So the range of photocurrent is going to be very less, very you can say minimal. It is in the range of microampere. Why? So because photocurrent are not going to be you can say produced in that much number, so we can get a current in ampere, or we can even get a current in milliampere. Clear this thing? This particular point is clear or not? The next point is the experimental arrangement given above, means the previous page, is used to study the variation of photocurrent with intensity of radiation, frequency of radiation, and the potential difference between plates and C. Obviously, the maximum, if we put a higher potential, so the flow is going to be more, isn't it? Why? In this page, you can understand. If the potential of this particular, I mean this particular potential difference, if this particular potential difference V is going to be high. Okay, let's understand more about it. If V is high, okay, so what is going to be done then, beta? If V is high, so obviously, or you can say the potential difference between plates, if V, potential difference between plate C, between plates C and A is high. Okay, if it is going to be done between plates C and A is high, so C and A have more negative or positive charge on them. That is the meaning of saying this. What does it mean? If the potential difference is high, and we know potential difference is what in general? Potential difference, the definition of a potential difference, work done upon Q. Clear? So if it is high, the difference is high. So obviously the charge difference is going to be more. Clear na? C is high, so C and A have more potential positive or negative charge on them, or basically the charge difference is going to be higher. So the charge difference is going to be higher. So what it states that it is going to be simply the more amount of flow. Basically the flow is going to increase. But the main point is, what I want to write here, the flow of photoelectrons is going to be high. And if the flow of photoelectrons is going to be high, so it is quite normal, the electric current is going to be high a little bit. Clear? Why so? Because in the previous class, even in this class, we are going to discuss KE max. KE max is nothing but E, charge on an electron, V naught, EV naught. Okay. So obviously, if V naught, the potential, or you can say stopping potential, the potential difference between the cell, between the plates is going to be high. So what it is going to be then? It is quite obvious. The kinetic energy means the flow of electron is going to be high. The flow of electron is going to be high means ampere or current is going to be high. And how your photo current, is going to behave with the intensity of radiation and frequency of radiation, we are going to see with this. Is this clear, everyone? Okay, so that is the effect of yeah. So that is the effect of intensity on photo current. Basically, the intensity is going to be directly proportional. Okay, more the intensity, more the amplitude, more the number of photo electrons going to be generated. Why so? Because in the previous class also, intensity is directly proportional to the amplitude square basically. Okay, means you can understand in this way. Just a minute. If there is a photo electric process is going to be, or you can say if there is a material and the intensity on this particular material is going to be high. Okay, in this way. So obviously the more number of photo electrons is going to be generated. The more number of photo electrons is going to be generated. And if the more number of photo electrons is going to be generated, so basically I equals to Q by T, right? I equals to Q upon T, and we know Q equals to NE. Q equals to NE. So this N is increases, or this N is dependent with high intensity. With high intensity source. Clear this one? Clear na? Because the more intense light is going to be hit any particular material or a photoelectric material, so that is going to generate a huge or large amount of photocurrent. Clearly? Is this clear na? Means more intense, you can write in this way also, intense. More intense light gives us, more intense light gives us huge, gives us huge amount of photoelectrons basically. Photoelectrons. Or what is photoelectrons? The electrons which are generated by the P effect. Clear? And if we have a more amount of number of electrons, so basically we can, this intensity is going to be directly related. So for a fixed frequency, and that is going to be fixed frequency. And what is a fixed frequency? Fixed frequency is that particular frequency which is a threshold frequency. For a fixed frequency of incident radiation and accelerating potential, means the two things going to be fixed, frequency and accelerating potential. The photoelectric current increases linearly with the increase in the intensity of incident light. Why so and how so? As photoelectric current is directly proportional to the number of photoelectrons emitted per second. Clear? And that what I discussed since last 2-3 minutes. The number of photoelectrons basically, or photoelectrons emitted per second is directly proportional to the intensity. So the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. Clear na? So the more number, more electric current is going to be generated, and that electric current is basically photoelectric current, and that is why we can get this direct relationship between the intensity of light and between the photoelectric current. Is this clear, everyone? This is quite basic, quite understanding, quite obvious to know. Clear na, everyone? I just give you the detailed explanation why it is going to be. Clear? Moving ahead, effect of potential on photoelectric current. Okay, so potential, or you can say retarding potential basically. For a fixed frequency and intensity, let's discuss what it is written over there, and then I am going to explain the graph also. So beta, for a fixed frequency and intensity of incident light, photoelectric current increases with increase in potential applied to the conductor as shown in the graph. Means the photoelectric current is going to be increases, obviously I1, I2, I3. If I increase this difference regarding the potential. Okay, means this V naught is give you more amount of electric current. Why so? How so? We discussed, even I discussed very previously on the first page, like the more potential difference, more difference between the charges on plates, more difference between the charges on plates. So what we have then, the flow is going to be more. So when flow is going to be more, now the reverse psychology is going to play. Suppose this is my photoelectric current IPE, that is going to be Q divided by T. Okay, understand in this way, Q divided by T. So obviously Q here going to be any fix, because I fix the intensity and frequency. When I fix the intensity and frequency both all together, so how this is going to be increases? As you can see, this is my vacuum chamber. In this vacuum chamber, this is the plate C, where the number, or you can say intensity, is going to be it, and this is the plate A. Okay, this is plate C, this is plate A, and suppose appropriable, I mean, which basically generate the photoelectrons, is going to increase in this way. But increasing the potential, but applying a high potential, what I can do, then with this, there is you can say more negative charge and there is more positive charge. So obviously if I have more positive charge on plate A, so the flow of electrons is going to be increased, isn't it? This flow of electrons going to be increased. So beta, when flow increase, what we can understand, due to high potential difference, the flow of electrons increases, the flow of photoelectrons increases, the flow of photoelectrons increases, the flow of photoelectrons increases. So beta, when flow of photoelectrons increases, the length remains same. Okay, try to understand this thing. This is very common, obvious. This length remains same, and I'm saying V increases. Flow is what? Velocity of photoelectrons increases. So automatically, if the velocity of photoelectron increases and the length remains same, so time needs to be less, isn't it? Why so? Because we know velocity of electron, VE, length upon time. So length remains same, V increases, so T has to be decreased. And the increases, automatically my current increases. Is this clear, everyone? So due to high potential difference, the photoelectrons increase their speed, or you can say flow. Basically VE is going to be L by T. L by T. L remains same. So automatically, so T is going to decrease, as simple as that. Okay, and when T is going to decrease, so automatically from equation 1, I is going to increase. Clear na? I'm not going to write this everything single line by line, but it is quite general to understand, because once I made my this vacuum chamber, so I cannot change or I cannot alter the length again and again, because creating a vacuum chamber with creating a vacuum plate, or this is my vacuum chamber basically. Okay, creating this vacuum chamber is a costly thing, so I'm not going to alter its dimension. Obviously if I'm not altering its dimension, so length remains same, isn't it? So when this length is going to be remain same, so when this length is going to remain same, but speed in between them is going to be increases, so automatically time is going to be decreases. Clear enough? This thing is clear enough now? Okay, this is stopping potential. What it is? Obviously, I am increasing the potential, but what this instead for? I mean, this stands for the stopping potential. What does it mean? Means it is that minimum bare potential which you need to apply to get out of this photoelectron, to get one photoelectron, or to get in emission of photoelectron. Is this clear? Okay, so this is, wait a minute, I think this is necessary. Okay, okay. So this is about the this variation. Okay, everyone, is this clear? What I'm I mean, make you understand. Try to make. Okay, everyone. Pavan, Sai, Sudarshan, Adayan, Yadira. Okay. So now this is the effect of potential on photoelectric current, and let's discuss this. So from the graph we can observe that after certain value of accelerating potential, when all photon electrons reach the plate A, the photoelectron, or you can say the photocurrent, ceases on the increasing the value of accelerating potential. The maximum value of photoelectron is called saturation current. Means, as you can see, after increasing to a certain point, each particular current, each particular current can get a saturated point. Even they are get the higher range, or you can say higher order, but they become the saturated. Okay, so that is what it is written over there. The second point, when the potential is decreases, the current decreases but does not become zero. Okay, means when potential decreases, so current decreases but does not become zero at zero potential. This shows that even in the absence of accelerating potential, few photoelectrons manage to reach the plate A on their own line. Means even if you don't apply this particular potential difference, still when any particular photoelectric material is going to be, you can say, put in presence of any particular source light, so the source light is going to be a little bit higher, so it can give both the things, the threshold energy and as well as the kinetic energy. So that using that kinetic energy from the source light, from the source in intensity, from the source energy, that particular photoelectrons is able to overcome the distance between the plates, but it is not able to get continuous, or it is not able to make the continuous flow. Is this clear now, everyone? Clear? The third point is, for a particular frequency of incident radiation, when minimum negative potential V0 is applied to the plate A with respect to C, the photoelectric current becomes zero at a particular value of negative potential V0, called stopping potential or cutoff potential. So from this particular graph, after applying certain negative retarding potential, it is going to stop. It is what it is here, current, photoelectric current. So that particular potential is known as stopping potential, means the current at that particular potential is going to stop, or the cutoff potential. Is this clear with everyone? Clear, everyone? Everyone, I'm asking. Other than Yajira, like Sudarshan, Pavan, Sai, Sakti. Clear? Means whatever we discuss on the previous page, that is, we write it down in the number of points or using the bullets 1, 2, 3. Now this is effect of potential on photoelectric current, and we already discussed this thing, but still again, in this condition, the stopping potential is sufficient to repel even the most energetic photoelectron with maximum kinetic energy K max. Okay, means at stopping potential, that particular potential is, I mean, that up to the mark, or that is that much, so it can create a repulsion effect for maximum kinetic energy, or for a moving fast photoelectron which is moving with Vmax. Okay, so photoelectric current becomes zero whenever no electron, even the fastest photoelectrons, can reach the plate A. Hence, the maximum kinetic energy is given as Ke max, or you can say K max EV naught, that is half mv square max, where m is the mass of the photoelectron and V max is the velocity of emitted photoelectrons. Means we have a certain potential at which even the highest moving, or you can say the fastest moving electron is going to be stopped. Clear everyone? And that is known as stopping potential, and that is why it is the name of stopping potential. So the maximum kinetic energy, or K max, can be equal to the EV naught, and that is very, very important relation. Clear, beta? Now this is effect of frequency, or you can say effect of frequency of incident radiation on stopping potential. Means if I change the frequency, so how the photoelectric current is going to be behave. So if we take radiations of different frequencies but same intensity, okay, we reach, for each radiation we study the variation of photoelectric current against the potential difference between the plates as shown in the graph below. I mean in this side, variation of photoelectric current versus potential for different frequencies but constant intensity of incident radiation. So somehow this is, I mean, your look like graph is going to be after a certain region or after a certain point. It is not actually correct. It is going to be somewhere in this way, and then somewhere in this way, and then somewhere in this way. So after a certain point, it is going to be constant. Okay, I mean this single line, obviously you cannot get like this. After a certain range, they become a constant in this way. Clear everyone? So that is, let me move this in. This is going to be the saturation. This is going to be the saturation current. So what we can observe from this, we can observe one thing. The variation of photoelectric current is going to be differ with the different frequencies, and for different frequencies we have different potential difference, stopping potential. Okay, for different frequencies we are going to see the different stopping potential, nothing more than that. Even after getting some time, the saturation current is going to be, the current is going to be saturation, and it is going to look like this. The more you can say frequency, the more potential difference or stopping potential we can see. Clear? And why so? Because simply we know this relation E equals to H nu. Understand in this way, E equals to H nu, right? This is we know. From the simple basic relation you can correlate how and why we get this. E equals to H nu. Nu here is beta frequency. It is not velocity. Don't confuse with this. Quen Quen. Okay. So when frequency is high, obviously kinetic energy is high. Why so? Because W naught is fixed for material. This is fixed. We know this. Fixed. Fixed for a material. For a material. For a material. Okay. So beta, if it is fixed for a material, then your Ke max is going to be H nu minus W naught. Suppose this is something one value. So the more the frequency, the more kinetic energy. The more kinetic energy is, the more electron potential. Okay, how can I write? And we know Ke max, and we know Ke max is EV naught. Okay, so from this two relation, EV naught is going to be H nu minus W W naught is fixed. You can say any constant C. So beta V naught is going to be 1 by E. Then V naught stopping potential is going to be 1 by E H nu minus C. C is a constant. So obviously this V naught is directly proportional to not this V naught is directly proportional to mu. Here on the left hand side, okay, these look like same but not same. On the right hand side we have a frequency, on the left hand side we have a stopping potential. So in this way you can understand also. But after reaching a certain point, the current is going to be what? I mean, once we increases potential enough, so basically the kinetic energy is going to be maximum, and at maximum kinetic energy the saturation current is going to be we visualized or we see. Is this clear everyone? Clear now beta? So that is what it graphs states, that as you can see, for higher frequency we have higher stopping potential, and we can get from this relation. Okay, and you can write this equation also. This equation number, first, second, third, whatever the name you want to put. This is the relation between stopping potential and the frequency. And C here, you can either you can put C or either you can put W naught even, which is the work function. Okay. W naught. Clear everyone now? Good. Next thing is effect. I mean, whatever the effect we have seen on this, we are just going to discuss it. So let's do this in a proper written way. From the above graph, we observe that the value of stopping potential is different for radiation. You can say for different radiation, for different frequencies, but the value of saturation current for a given intensity remains constant. So that is quite obvious. The saturation current is more dependent on the intensity of light. Why it is more dependent on the intensity of light? Because intensity creates more number of electrons. So that is the saturation current is more dependent on the intensity. But we have find the relation between stopping potential and this particular thing, which is your frequency. V naught is 1 by E H nu, or I can write HF minus W naught. So using this relation, I can rewrite this using this relation number 2. What we can get, my V naught, the stopping potential. Okay, I can write this also. This is stopping potential. Stopping potential is directly proportional to the frequency. So the higher the frequency, the lesser is this. Negative sense. Okay, the value of stopping potential is more negative. The value of this, the value of stopping potential is more negative for incident radiation of higher frequency. This means that the energy of the emitted electrons depends on the frequency of incident radiations. Greater the frequency of the incident radiation, greater is the maximum kinetic energy of photoelectrons. Obviously, we discussed this thing. Okay, and consequently, greater retarding potential or stopping potential is required to stop them completely. Simple thing. Work function is fixed for a material. So more intensity going to give you more number of electron, more frequency going to give you Ke max. More Ke max, more in negative sense you need to apply the potential, which is known as retarding or stopping potential. Is this clear everyone? Is this clear beta everyone? Okay, the next thing is, just a minute, the third effect. Okay, so these are the two effects, and the value of saturation current we already discussed them. So let's not do this again and again. The value of saturation current depends upon the intensity of incident radiation, but is independent of the frequency of the incident radiation. Okay, so saturation current is independent of, you can write in this way, I saturation is directly dependent on intensity. Intensity. Okay, I saturation is current saturation, where saturation current, I saturation, or you can say air saturation current, air saturation current, I saturation is independent, independent of frequency. Okay, clear? So that is already written there. I just rewrite into the my words, or you can say into the symbols. Nothing more. Now, effect of potential, effect of frequency of incident radiation on stopping potential. So we can see that if more the frequency, more the stopping potential is going to be. This V naught and V naught prime is what it is for metal A, for metal B. That you can say stopping potential, the threshold you can say that particular thing, after which the photoelectrons is going to be emitted. Okay. So if we plot a graph between stopping potential and the frequency of the incident radiation for two different metals A and B, we get the graph as shown, and this is the graph. Okay, so from the graph what we can see, we are going to see on the next page, and then the law of photoelectric emission we are going to discuss after a short break, because so much I need to speak in this. So from the graph we observe that the stopping potential V naught varies linearly with the frequency of incident radiation for a given photosensitive material. There exists a certain minimum cutoff frequency V naught for which the stopping potential is zero, and this frequency is called threshold frequency. So that is the main thing. This is, these are basically what it is. These are basically the threshold frequencies. These are basically threshold frequency. Okay, frequencies for metal A and B. Clear? This is a minimum bare and that minimum bare frequency after which it is going to give a photoelectron, that is threshold frequency. Okay, beta. Why this is speaker? Okay, let's take a break for 10 to 5 minutes, and I know this is going to be completed meanwhile till 9 or 9, 10, 5, 5 max to max, because after this law of we have photoelectron wave theory, and then there are questions, and then they are going to see the CA and SW. Clear? Not much is remaining, so that's why I give you a break. Hello, hello, hello. Am I audible? Hello. Hello, hello, hello. Just a minute. Stay there. This is in Hindi. I want to see this. Just a minute, beta. I'm searching something for you. Just a minute. That is. That is perfect. Okay. I'm going to. Yes, sir. You are audible. Okay. I'm going to show you a video. Okay. Just meanwhile, let me raise this. That is going to give you a more clarity what it is all about, and then we are going to discuss cancel once, because then you are going to see this. Okay. Yeah.
इस वीडियो में हम समझेंगे फोटोइलेक्ट्रिक।
Is this visible to you guys? Clear now, everyone? It may be in Hindi, so can I? Yeah, subtitle you can be turn on. Annotations, yeah, annotations. Now you get
इफेक्ट।
you can.
फोटोइलेक्ट्रिक इफेक्ट एक ऐसा फेनोमेनन है जिसमें लाइट रेडिएशन किसी मेटल सरफेस पे फॉल करती है और
Just try to visualize, and obviously if you can understand a little bit Hindi, so you can do that, and if you don't, so just visualize what it is happening in this effect. Okay.
मेटल सरफेस से इलेक्ट्रॉन एमिशन होता है। इस फेनोमेनन को जर्मन फिजिसिस्ट हेनरिच हर्ट्ज ने 1887 में डिस्कवर किया था। जब हेनरिच हर्ट्ज इलेक्ट्रॉन मैग्नेटिक वेव से रिलेटेड एक्सपेरिमेंट कर रहे थे, तब उन्होंने ये पाया कि जब भी अल्ट्रावायलेट लाइट को दो मेटल इलेक्ट्रोड्स पे फॉल करे और दोनों इलेक्ट्रोड्स पे वोल्टेज अप्लाई किया जाए, तो दोनों इलेक्ट्रोड्स पे स्पार्किंग होती है। इस फेनोमेनन को आगे स्टडी करते हुए 1902 में जर्मन फिजिसिस्ट फिलिप लेनार्ड ने इस ऑब्जर्वेशन को एक्सप्लेन किया। उन्होंने ये बताया कि जब मेटल सरफेस पे लाइट फॉल करती है, तब मेटल सरफेस से चार्ज पार्टिकल्स लिबरेट होते हैं। इस एक्सपेरिमेंट से पहले लाइट को वेव माना जाता था, लेकिन फोटोइलेक्ट्रिक इफेक्ट की डिस्कवरी के बाद ये पाया गया कि लाइट में पार्टिकल नेचर भी होता है, और इसी कारण क्लासिकल फिजिक्स इस फेनोमेनन को एक्सप्लेन नहीं कर पाई। 1905 में एल्बर्ट आइंस्टाइन ने कॉर्पस्क्यूलर थ्योरी को डिस्कवर किया, जिसमें उन्होंने बताया कि लाइट में वेव नेचर और पार्टिकल नेचर दोनों होता है, और लाइट में जो पार्टिकल होते हैं उसे फोटोन कहते हैं। कॉर्पस्क्यूलर थ्योरी की मदद से एल्बर्ट आइंस्टाइन ने फोटोइलेक्ट्रिक इफेक्ट की एक्सपेरिमेंटल स्टडी की और इसे एक्सप्लेन किया, जिसके लिए उन्हें नोबेल प्राइज भी मिला। तो आइए इस फेनोमेनन को डिटेल में समझते हैं। एनिमेशन में हम देखते हैं कि एक एवैक्यूएटेड ग्लास ट्यूब है। इस ट्यूब के एक एंड पे एक फोटोसेंसिटिव प्लेट है और दूसरे एंड पे एक मेटल प्लेट है। ग्लास ट्यूब के ऊपर एक ट्रांसपेरेंट विंडो लगाया गया है। ये ट्रांसपेरेंट विंडो लाइट को फिल्टर करके एक पर्टिकुलर वेवलेंथ की लाइट को पास करता है। मेटल प्लेट और फोटोसेंसिटिव प्लेट को एक वोल्टेज सोर्स से कनेक्ट किया गया है, जिसमें मेटल प्लेट पॉजिटिव टर्मिनल और फोटोसेंसिटिव प्लेट नेगेटिव टर्मिनल से कनेक्ट है। इस वोल्टेज सोर्स से डिजायर्ड वोल्टेज आउटपुट लिया जा सकता है। अब हम एक मोनोक्रोमेटिक लाइट सोर्स से लाइट रेडिएशन एमिट करेंगे। ये लाइट रेडिएशन ट्रांसपेरेंट विंडो से फिल्टर होने के बाद फोटोसेंसिटिव प्लेट पे फॉल करती है। जैसे ही रेडिएशन फोटोसेंसिटिव प्लेट पे फॉल करती है, वैसे ही प्लेट से इलेक्ट्रॉन्स एमिट होने लगते हैं। ये इलेक्ट्रॉन्स मेटल प्लेट की ओर एक्सेलरेट होते हैं और आउटर सर्किट में फ्लो करने लगते हैं, जिसके कारण सर्किट में करंट क्रिएट होता है, और इस करंट को हम फोटोइलेक्ट्रिक करंट कहते हैं। इस करंट को माइक्रो एमीटर की मदद से मेजर किया जा सकता है। इस एक्सपेरिमेंटल स्टडी में ये पाया गया कि फोटोइलेक्ट्रिक करंट का वेरिएशन कुछ फैक्टर्स पे डिपेंड करता है, और ये फैक्टर्स हैं इंटेंसिटी ऑफ रेडिएशन, पोटेंशियल और वोल्टेज ऑन मेटल प्लेट, एंड फ्रीक्वेंसी ऑफ रेडिएशन। आइए अब जानते हैं कि ये फैक्टर्स फोटोइलेक्ट्रिक इफेक्ट को कैसे अफेक्ट करते हैं। इफेक्ट ऑफ इंटेंसिटी ऑफ द इंसिडेंट रेडिएशन। इस एक्सपेरिमेंट में ये पाया गया कि फोटोइलेक्ट्रिक करंट रेडिएशन इंटेंसिटी के डायरेक्टली प्रोपोर्शनल होता है। कहने का मतलब, जितना ज्यादा रेडिएशन की इंटेंसिटी होगी, उतना ही फोटोइलेक्ट्रिक करंट जेनरेट होगा। इफेक्ट ऑफ पोटेंशियल ऑन मेटल प्लेट। इस एक्सपेरिमेंट में ये पाया गया कि फोटोइलेक्ट्रिक करंट पोटेंशियल यानी वोल्टेज।
Beta, just wait for a while, Sai. I cannot stop video for you all alone because everyone is watching that. So I can send you the link after a while. Got it? And you can refresh because I think everyone is able to see that.
कोई इंक्रीज नहीं होता। इस मैक्सिमम करंट की वैल्यू को हम सैचुरेशन करंट कहते हैं। अब अगर हम वोल्टेज की डायरेक्शन को रिवर्स कर दे तो हम देखते हैं कि फोटोइलेक्ट्रिक करंट डिक्रीज होने लगता है, और अगर ये रिवर्स वोल्टेज लगातार बढ़ता जाए तो एक पर्टिकुलर वैल्यू पे फोटोइलेक्ट्रिक करंट 0 हो जाता है। इस नेगेटिव वोल्टेज की वैल्यू को हम स्टॉपिंग पोटेंशियल कहते हैं। इफेक्ट ऑफ फ्रीक्वेंसी ऑफ रेडिएशन। इस एक्सपेरिमेंट में ये पाया गया कि जब सेम इंटेंसिटी की रेडिएशन को डिफरेंट फ्रीक्वेंसी के साथ फॉल किया जाए तो फोटोइलेक्ट्रिक करंट और स्टॉपिंग पोटेंशियल की वैल्यू डिफरेंट होती है। थैंक्स फॉर वॉचिंग। अगर आपको हमारा ये वीडियो अच्छा लगा तो ऐसे ही और वीडियो देखने के लिए चैनल को
hello. Yeah, this is the video link. Okay, the student who are not able to see that, you can go through. Clear? So in this video, whatever we learn, we can see, we can visualize what it is going on, and you can get the clarity effect of intensity. Like intensity going to give you direct relation because the number of electrons is going to be, and if we increase this photoelectric, you can say this potential, negative potential basically, which is known as a stopping potential. So at a particular potential, the current is going to be, which is the photoelectric current is going to be stopped, and that is particular potential is known as stopping potential. Okay, now we are going to discuss the laws of photoelectric emission, and the laws of photoelectric emission are as follows. For a given material, I mean, whatever we done, whatever we know, we are going to formulate this particular, you can say, known thing into the form of laws. So the first law is, for a given material and a given frequency of incident radiation, the photoelectric current or number of photoelectrons ejected per second is directly proportional to the intensity of incident light. So with this, what we can understand, the number of photoelectrons, okay, is directly proportional to the intensity. Nothing is going to be new here, where n you can write number of photoelectrons, as simple as that. Number of photoelectrons. Is this clear, everyone? Clear now this thing? Since the beginning we are learning this, nothing new. For a given material and a frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of its intensity. Wait for a while. What does it mean? Means as saturation current is directly or proportional to the intensity of this particular thing, intensity of a radiation of light. Okay, so again in writing sense, I saturation is proportional to the intensity of radiation. Intensity of radiation. Intensity of radiation, and you can say is proportional to the intensity of radiation, whereas the stopping potential is independent of intensity. Okay, stopping potential, which is V naught, stopping potential, which is V naught, is independent. Independent of what, beta? Independent of intensity, or yeah, intensity I. Clear, everyone? So this is the two important things. Okay, after that in the same way we have another points. Let's discuss all this also. So third thing, for a given material there exists a certain minimum frequency of the incident radiation below which no emission of photoelectron takes place. This frequency is called threshold frequency. So what we know, F naught, basically the minimum, or you can say threshold frequency. And what is the threshold frequency? Threshold frequency. What it is, beta? Threshold frequency. Threshold frequency is the minimum bare frequency below which any particular incident radiation cannot able to eject photoelectrons. As simple as that. Okay. Above the threshold frequency, the maximum kinetic energy of the emitted photoelectrons or equivalent stopping potential is independent of the intensity of the incident light, but depends only on the frequency or wavelength of incident light. Okay. If my incident radiation doesn't have equal or greater than this threshold frequency or the wavelength, so the emission or ejection of photoelectron is not able to. Is this clear, everyone? Clear now? The photoelectric emission is an instantaneous process. The time lag between the incidence of an radiation and emission of photoelectron is very small, less than the 10 to the power minus 9 seconds. Okay, so what does fourth point stands for? PE effect is very fast, or you can say instantaneous process. PE effect is instantaneous process. Instantaneous process, and time lag, or you can say instantaneous process means time duration to eject an electron. Time duration to eject an electron is 10 to the power minus 9, or you can say 10 nanoseconds. 10 nanosecond is exactly 10 to the power minus, or you can say 1 nanosecond instead of 10. 1 nanosecond. Clear? 1 nanosecond stands for 10 to the power. Just 1 nanosecond. 1 nanosecond. What does it mean? 10 to the power minus 9 seconds. Clear, everyone? Okay. These 2 points are clear now. Good. The next thing is photoelectric effect and wave theory of light. So Huygens wave theory of light could not be able to explain the photoelectric emission due to the following main reasons. So previously, in the previous chapter, we can say the chapter before this, what we learned, the wave theory or Huygens wave theory, means we study light have a dual nature, the particle nature as well as the wave nature. So if we try to prove photoelectric effect with the help of wave nature of a light, so we are not able to do that. Why so? We are going to see in this particular points. So Huygens wave theory of light could not explain the photoelectric emission due to the following main reasons. And the main reasons are as such. According to the wave nature of light, the free electron at the surface of the metal absorb the radiant energy continuously. Why so? Because each particular secondary wave is, or you can say each particular wave is the source of new secondary wavelets. So if it is the source of new secondary wavelets, beta, so what is going to be in general, the energy transformation is going to be stick easily. So the process of emission of photoelectric, emission of photoelectrons is not going to be, you can say, see there. Why so? Because the wave front, or you can say the wave theory, tells the transfer of energy only. That energy is not going to utilize in this form. The greater the intensity, okay, the greater the intensity of a radiation, the greater should be the energy absorbed by each electron. The maximum kinetic energy of photoelectrons on the surface is then expected to increase with increase in intensity. Means, if we consider a light as a wave, so what it is just going to increase the thermal energy of a material. Why so? Because when light is incident in the form of waves, so the vibrational motion in between the atoms or molecules or electrons is going to be more. So this vibrational energy can be converted into the heat energy, and what we can see in day-to-day life. For example, whenever we put any particular object, or you can say anything, into the, you can say, bright sunny day or in a full sun rays, so the heat energy, or you can say the object is getting heated up. Clear? And you can observe simply when you can say automobile or specifically a two-wheeler is parked in an open area, in an open parking anywhere. So the seat of that particular you can say automobile or specifically bikes and scooters going to be very, very hot in the summer days, right? Why this is not going to show this particular effect, which is P effect? Because there the energy is transferred into the form of waves as a light, and that particle or that material itself is not convert or not eject the electron. Basically, the material is not giving you free electrons. Okay, they just start moving randomly or with a high energy, and the vibration is going to be more and more. What does it mean? Means if it is an atom at atomic level, we are saying, okay, suppose it is an atom, one cell, second cell, and this cell. So when this phenomenon is going to be done, okay, so these electron is basically start rotating with higher speed, and with these electrons start rotating with higher speed. So basically what happens, this is an atom and molecule is containing, you can say, large number of atoms like this. So the number, suppose, okay, wait for a while, suppose this is one atom, this is another. Obviously atoms needs to look like same, but let's suppose in this way we can see that, okay, there is a nucleus. In this way we can see that, not this color, okay. In this way we can see that, suppose there is a material, okay, and in this material the light intensity is going to be 8. So these basically start vibrating with higher order, and when these electrons start moving or vibrated with higher order, so simply what we can see, what we can feel, the heating up of the object and the heating effect of a body. Okay, means these electrons are not able to lose their valence shell even. They just start vibrating more, and due to this vibration, due to this, you can say, more energy into the form of waves, it is going to be heated up. Okay. So, but according to experimental facts, the maximum kinetic energy of an ejected photoelectron is independent of intensity of radiation. So, experimentally, we've seen that kinetic energy is not related to the intensity. So, a material is almost dependent, and the kind of a light which we are going to use. I mean, kind of a light means what particular nature we are going to see with the light. The particle effect, or you can say the photons effect, and the photons nature, particle nature, or the wave nature. Clear now, everyone? Now, according to the wave theory of light, no matter what the frequency of radiation is, sufficiently intense beam of radiation should be able to impart enough energy to the electrons so they exceed the minimum energy needed to escape from the metal. Whatever I discuss, whatever I said with this drawing, that is actually written on the next point. Is this clear? Okay, means considering, you can take as a screenshot of this, and I can paste here as well. Yeah, taking, I mean, this is again I can draw. Taking this particular diagram, what you can understand, taking wave nature of a particle, I mean the point second, this is the diagram related to point second. Taking, not this again, taking wave nature of a particle. Wave nature of a particle. Okay. So if particle wave nature of a radiation or source. Source or radiation is basically light, right? So if we are taking the wave nature of a radiation, which is a source here, clear? So what we can see, according to the wave theory of light or a radiation or a source, no matter what the frequency of radiation is, no matter how much frequency is there, is a sufficiently intense beam, I mean, or a sufficiently intense beam, even the intensity is going to be very, very high. And you can see that you can say in the hot summer day, the intensity of the sunlight is very, very high, right? Means if you put a water in that, so the water is going to be boil even that much intense, should be able to impart enough energy. Means that intensity or that intense or that high frequency light is not able to impart energy, enough energy to separate the electrons. And if it is not able, because we take a wave theory. So this thing, a threshold frequency, therefore should not exist, which contradicts the experimental fact that no photoelectric emission takes place below the threshold frequency, no matter whatsoever may be the intensity is. Clear? If we consider the wave theory, so there is no such concept of threshold frequency. And if there is no threshold frequency there, so obviously the ejection, the emission of photoelectric particle, or you can say photoelectron, is going to be zero. And if the ejection and emission of photoelectrons is zero there, so obviously there is no photoelectric effect, isn't it? Is this clear now, beta, what I'm saying? Clear? Means if we consider the wave nature of a light, so there is no concept of least minimum frequency, which is known as threshold frequency. If there is no threshold frequency, so the material cannot give you any kind of photoelectron, or it is not going to emit, it is not going to eject anything in this sense. So we cannot get any photoelectric effect. Okay, and in this way we are done today. Wait. According to wave theory, one point we have still. Let's discuss over this also. According to the wave theory of light, the absorption of energy, that is also important one. Okay. According to the wave theory of light, the absorption of energy by electron takes place continuously over the entire wavefront of the radiation. That I already tell you in the beginning. Whenever we take the wave theory, so the energy is going to be continuously taken by the next wavefront. That is the process of wavefront. Means one wavefront is the, you can say, is going to produce the next wavefront. How so? Why so? By the flow of energy. As simple as that. Since a large number of electrons absorb energy, the energy absorbed per electron per unit time tends to be very small. Hence, it will take hours or more for a single, hour or more for a single electron to come out of the metal, which contradicts the experimental fact the PE effect is instantaneous. So if we take, that is important even, this para alone, if we take the wave nature, so to give the energy in the form of wave nature, in the form of wavefront, single electron can take hours or amount or more amount of time to just get emitted. And if it is in that way, if it is get a more time to just get emitted, so what we can see, there is no as such PE effect is instantaneous. But with the help of a diagram, with this video, you also can see that, visualize that PE effect. Okay, beta, you can leave it in the that video also, or in the theory also, or experimentally also, we can see that PE effect is instantaneous. Means the moment your light is going to hit on a very second, another, even at the range of micro or nanosecond range, the PE effect or the photoelectric current we can observe experimentally. So that is not going to be proven by the wave theory. Okay. So this is done for your today's. This is very simple question. The photoelectric cutoff voltage in a certain experiment is this. What is the maximum kinetic energy of a photoelectron? Questions like this you can get, nothing more and so. Do these two questions and then we are going to do the class assessment. Very easy. Okay. Cutoff voltage means stopping potential you have in your hand. You need to find the maximum kinetic energy of photoelectrons. Do that. Is this clear, beta? Tell me the answer then. Today's class we try to finish before 9 or till 9. Okay, we have still half an hour. Do that these two questions and then we can do class assessment. And I can tell you few questions as a class assessment. 2.4 into 10 to the power minus 19. 1.5 into 1.6. Okay, so that is very easy. As we know this, given cutoff voltage is this 1.4 volt. Maximum kinetic energy is given by Ke max EV naught, and that is 1.5 EV naught, and that is your maximum kinetic energy. Clear, everyone? Or anyone have a doubt, question, query, even for this also? Other than Yadira, everyone, please, Pavan and Sai and Dharmeshwar and Sakti and this Sudarshan student. Clear na beta? Hello. Understood. Okay. The work function of a certain metal is this. Will this metal give photoelectric emission for incident radiation of wavelength distance? Okay. So tell me if it is or not. So work function is given, lambda is given. With the help of lambda, you can find energy. And if the energy is lesser than this, so you can do that. And if it is not, so you can do that also. One formula I can give you directly. Just a minute. I need to apply this. Sometimes continuously you using these headphones. Okay. You can use this E equals to Hc by lambda, right? And when lambda is in NF, so the value of Hc is 1240 eV Nm. Okay. So you can use this. When lambda is in Nm. Nm stands for nanometer. We can use this. Okay. Now it is very easy. Do that, solve that, and tell me the answer. Everyone, I want answer for this. Everyone, I'm not going to show you. One by one, do that. Meanwhile, I can open your this CANSW. Tell me the answer. It is 6 into 10 to the power 21. Huh? How it is going to be? I tell you to use this formula, na? why do you use still this 10 to the power minus 17 and so and so? Why should I tell you this? Lambda is in nanometer, na? So automatically, if your energy is going to be more than the work function, obviously it is less than the this. So, but how it is? Three point seven. Yes. Okay. So this is how given phi is this, which is 4.2 into 10 to the power this, or you can say 6.72 into 10 to the power. Either you can convert this or either you can use this. But that is important. You can use 12.0 EV when lambda is up to the range of nanometer. Okay. So even with this, you can see that put the value of electron volt, which is 1.6 into 10 to the power 9. So phi you can get this, and putting this and using this every value, because H have 6.63 into 10 to the power minus 34, and C we already know 3 into 10 to the power 8 meters per second. Okay. So we are done for the today's class. In this particular theory lecture, we do the effect of intensity light on photoelectron, photocurrent, effect of potential on a photoelectric current, or effect of frequency of incident radiation, and on stopping potential and wave theory.